Section 2.3, 2.4, that'll be brief. So I do want to point out, you'll find that this will be really quick. And then we'll cover section 2.5. So we're like, okay, well what's 2.3? 2.3 is using the limit laws. The limit laws to evaluate a limit. Well, I'm going to write that another way. Use the limit laws to evaluate a limit. Okay, how about, you can just say, finding limits algebraically. That's probably a better way to think about it. Finding limits algebraically. Maybe that's a better title. So today we do algebra. Probably more so, we do a lot of algebra and calculus. But simplifying, every type of simplification you ever did in an algebra class will probably come to play today. 2.4, what's that title? Well, that's the precise definition of limit. That'll be brief. It's the precise definition of limit. Like, how do you really define the word limit? As precisely as possible, what do we do? That won't be too boring. And then this 2.5, that's just on continuity. So I'll put that here. 2.5 will be continuity. Continuity and 2.5. So that's what we'll be covering today. 2, 3, 2, 4, 2, 5. Anybody have questions? 2, 1, 2, 2. Any textbook problem? You got one?
Number 11.
Which section?
2.2.
So I went in 2.2. Let's go to number 11. Oh man, you're the best.
Alright.
I love that one. That one. I didn't do this problem last class. I'm so glad you brought this up. So we'll definitely emphasize that one. This was from 2.2, and this was a Professor Mestre. You forgot to do one like this. Of all the problems we did, this thing is a piecewise function. So they got f of x equals, I got the squiggly symbol, right? The little brace. They got three parts to this. There's a 1 plus x. They got an x squared. And then they got a 2 minus x. Then they've got if statements. If x is less than -1 is this part. For the x squared, they got if x is between a -1 but less than a 1. So between -1 and 1, including the -1. And then for the 2 minus x, they just got if x is greater than equal to a 2. Oh, it should be a 1, I apologize. Alright, if you want to put little commas here, you can. Little commas. So, this piecewise function, or piecewise defined function, it's 1 plus x here, it's x squared here, it's 2 minus x here, and after all that writing, they go sketch the graph of the function, use it to determine the values of a for which the limit exists. Alright? So we're going to define which values of a for which the limit exists. What we're going to do is, this is how I like to design this on tests, use these functions that exist everywhere, but we have to really check on this what? -1 and this 1, right? The critical numbers to see, is the limit existing if there's two numbers? So the way I'll word the question is basically the opposite. Can we define where the limit does not exist? Does that sound good? We're going to focus on that. Where does the limit not exist? But to get this going, what's an easy way to do this? Make a graph. So let's go ahead and make a graph of this. So let me just write this down. And when you and I have to find the x values, at which f of x is not continuous. There's another word for not continuous. You can just call it discontinuous. So I'll write that. Discontinuous. Right? Or which the limit does not what? We haven't gotten continuity yet. I'll do that at the end of class. Find the x at which f of x does not have a limit existing. And I mean a two-sided limit. existing. We're going to find the answer at which f(x) does not have a limit existing. Well, when you all know about y equals 1 plus x, that's a straight line, right? That's going to be safe everywhere. X squared is safe everywhere. That's a parabola, right? 2 minus x, that's another straight line. So do y'all agree we got 2 straight lines and a little parabola? Great. We're trying to focus on what's going on at what? -1, and what's the other one? 1. If we had to guess, we could just guess, okay, it's discontinuous at -1 and 1, you know? We'd be close. True. But we got to check these out. So one way to do it is graphical. We can make the graph. So let's graph this thing. It's not as bad as you think. We'll make this sketch. Let's start with that straight line, right? That's a straight line. I got to do it on x less than -1. But it doesn't have an equal sign. I still need you to plug that in and make that line. So if you want, you can just make a little table. Right? You plug -1 in there, what do you get? 0? Alright, give me one more value to plug in that so we can make a line, but go lower than -1. I use -2? Just to get the graph going. So I mean a little table, I'm just going to sketch that little line right there. I'll use -2. 1 plus -2 is what? Yep, 1 plus -1. So let's sketch that. At -1, it was 0. Alright. At -2, it was -1. Right there. Ah, negative slope, right? Or excuse me, positive slope. Going up from left to right. And there it goes. Hey, does anybody know why I'm keeping an open circle here? Does anybody know why I kept this little point open? It's because it didn't have the what? Equal symbol. So I kept an open circle. Yep. And this is your x-axis, that's your y-axis. One piece done, we just need 2 more pieces, right? Alright, parabola. Well, that's easy, x squared. Yeah, but still, let's make a little table. X, y. What 2 numbers should we plug in? Plug in a -1, see what you get. Plug in a little 1. That way we can just make the sketch. Just want to make a little sketch from -1 to 1, right? -1 squared is? 1 squared is? Ah, cool, that was easy. Which one's going to be open now? That side I'm going to close dot it. This side I'm going to, yep, so I'm going to keep this side open. All right. So at -1, it's a 1. Okay? Close dot. But at 1, I got to keep this open. It's going to be a positive 1 like that. But a parabola does a little hook, doesn't it? Almost done. Hey, I bet you already know one of the answers to this question from what we have so far. Can you all spot it? At which value do we already know it doesn't exist? The limit. Remember for limits, the left-sided limit has to equal the right-sided limit. And what I'm saying there, Chloe or Colin, is like, when we look at these graphs, as I approach -1 from the left side, the number it's got to match is the number it approaches from the right side. And we can see they're not going to the same spot. So the limit definitely, we're going to write it down, the limit definitely does not exist at -1. But now we got to check 1. So we'll finish the graph. Everyone okay on those 2 pieces? All right, one more piece. Plug in a couple points into that guy. Make a little table. All right, let's plug in a 1. And then we'll plug in a 2. 2 minus 1 is 1. 2 minus 2 is 0. And close dot it, right? Okay. Now I'm going to plot this point first. There's the 2, 0. Notice what's happening here. I'm plugging 1, 1 where there was an open circle. So what happens to the open circle? It gets closed up. That's right. See that open circle that I had before? It gets closed up. It just got closed up. Aha, the graph is, we'll get to that later today. The graph's continuous. Continuity, the graph's continuous here. It's not continuous there. So everyone, let's go on -1, limit does not exist. How about at 1 now? Well, does the graph approach the same value from the left as it approaches from the right? Cool. Do you see that, Chloe? It's like, oh cool, it's like, look, as you approach 1 from the left, you're approaching a 1. As you approach 1 from the right, you're approaching a 1. So the limit exists at 1, but the limit does not exist at -1. So the answer to this question, find the x values at which f(x) does not have a limit existing at x equal to -1. Hey, make a note, on your test. We don't meet Monday, but next Tuesday. I'll have a problem when you gotta do something like this, but it's gonna do with continuity. It's gonna be continuity, and you go, oh, but it's gonna be basically the same thing. You wanna make a sketch. Continuous is easy, just think connected. Find where the graph's connected. If it's not connected, it's not continuous. You know, we'll get to that later. We'll define it. We'll make a nice, nice precise definition of continuity, but just look to see where it's not connected. Where is it not continuous? So that you already have a sense of 2.5. It's not continuous at what? -1. Where is it continuous? Everywhere else, right? Same thing with limits. Where do the limits, now you go back to that question the book asked? The limit exists everywhere except for what? Everywhere except for -1. That was a good one. Thank you for bringing that up. I meant to do that one. I did. Hey, any others? So we definitely should do another one of these in 2.5, everyone. So let's come back to another one of these in 2.5. Cool. Hey, any other questions? All right. Hey, so we're going to hit it. Everyone, we're using the limit laws to evaluate a limit. Where are the limit laws? I mean, you like reading math textbooks? They've got them all listed. You go to page 99. Flip over to page 100. Get on to page 101. And then you'll see 11 limit laws. So what are you memorizing and stuff? I don't know. I think let's just jump into the lesson here, and I think you'll find that you can be okay with all those limit laws. Seriously, you can read through them. But the whole idea, this idea of finding limits algebraically is all these problems in 2.3, everyone, you're going to notice, deal with two-sided limits. Okay? And we're going to find the limit algebraically. So use the limit law to evaluate a limit. Well, how about this? Let's find the limits algebraically. But all these questions you're going to deal with, at least the majority of them, are going to be two-sided limit questions. Sound good? What if you have to do a one-sided limit problem? I just want to point that out first. Just be, hey, you got to find one-sided limit problems. What's the best way to do it? I don't recommend algebraically. What's two good ways to do it? One way is graph, right? These are my recommendations. Graphically. But what was the way we introduced right at the end of class last time? Tables, which is numerically. You can use either word, just try. So these are my recommendations. If you have to find a one-sided limit of an expression, and I say, well, look at the graph, it'll tell you the story, right? But also you can try it numerically. That's where you plug in numbers, like he said, a table. You plug in numbers really, really, really close to that endpoint to see what's going on there. And you'll find out what's going on with the one-sided limits. But what if you got these two-sided limit questions, like this? I'm going to start out. 2.3. We're going to do a limit problem. All right, when you got to find this, find the limit. As x approaches 2, x squared plus 3. I have a feeling you might like this section. So that's a two-sided limit, right? Well, now there are three ways to find limits. Graphically, numerically with tables. You can do it algebraically. I think you're going to prefer algebraically. Because you simply do what? You just plug it in. That's what you do. I mean, you can make the graph. You can look to see what's going on too, but that's what you're going to get. Cool. Just plug it in there. That's what we'll do. We haven't read through those 11 limit laws, but we get that. Plug in 2, what do you get? What's 2 squared plus 3? You go, it's that simple. Are you serious? That's the end of the lesson 2.3. I'm like, no. There's got to be some what? Weird scenarios, and we'll get to that. But I do want to point out, that's what you do. You got an algebraic expression, like I can just substitute 2. Get it? Because it's two-sided limit, I've got an algebraic expression, it's always safe. Well, what's the scenarios we really got to focus on today? Oh, you bet, fractions, right? Is that what you're going to say? Fractions. And in mathematics, when you get these fractional expressions, they call them rational expressions. So you're going to get a lot of rational expressions today. I want to make sure you're an expert. Okay, I'm going to put a lot of, they call them rational, sometimes they got radicals in there, and if it's got a radical in there, it's not rational, but it's still a fraction. Well, the key is in math, I'm going to put 3 numbers up here. Whoops. Set number. 0. That's 0. So I do want to point out, if you plug in the numbers like we just did, and you get 0 over 7, then your limit is 0. Cool. Here it's not though. What's going on here?
It's another number.
Non-existent, it's not a number. So if you get a value like this as your answer, then you're just going to say the two-side limit does not exist, it's non-existent. So what's the third scenario? Okay, let's go spend the next hour on this scenario. Because you'll get this, piece of cake. Like I said, it's like we can move on to the next section. This is the scenario we got to look at. That's called indeterminate form. Indeterminate form. Mathematicians went crazy with this form. Seriously, they just kept going, figuring out neat ways to solve limit problems when you get what's called indeterminate form. If you plug in that number, like we said, substitute the number into the algebraic expression. But if you get 0 to 0, then don't stop, keep going. Someone got that? Don't stop and say the answer is 0 because it isn't. The limit may exist. You'll keep going. So indeterminate form means you can't determine the answer right now. You got to do something to the expression. And you go, what do? We've used every tool we've used in our whole algebraic experience of our life. And we bring it into play. And we try to mess with it. We try to algebraically manipulate the expression. Okay? So if your algebra is kind of like what right now? Then let's do some review on some of these problems. Anyone okay with factoring? You'll see some factoring. You want to know how to add two fractions that the denominators aren't the same? You need a common what?
No.
Common denominator. Okay, we know that. Anybody in here ever multiplied a conjugate before? All right, you might have been a while, so we might do that too. We're going to use all these little tricks so that we can manipulate something if we get this. We can manipulate the expression, then substitute the number, and see what we get for the answer. Sound cool? These methods of graphing it still work. You can still pull out a graphing tool and graph it if you want to investigate it. Sometimes it's hard, you know, it's hard to see what that limit is, especially if it's irrational. So, here's my first one. All right, I want to find the limit. As x approaches 3, x squared plus 5x plus 6 over x minus 1. I don't know why everyone on the test, this problem seems to be everyone gets the hard ones. This one, students miss. I get a kick out of it. I always get a kick. They think they got to go and do all this algebraic manipulation and factor and all this stuff. They start factoring right away and stuff. There's no need for that, is there? We just talked about this. What can we do? Just what? Yeah, check this. I mean, we only have to manipulate if we get that 0 over 0. Then we sit there and go, okay. But if you get a number, that's your limit. So put it in there. I mean, you're not going to get 0, 0, are you? What's the denominator?
2.
2, and this is just some weird number. What is it? 9?
30.
Is it 30?
Yeah.
30. Can we reduce that?
Yeah.
There it is. Done. I'm laughing. I'm serious. I'm like, when I always go, I get to I'm like, oh my gosh. They got all the hard ones. And at the end, you start factoring this. They start seeing if they can cancel things, right? All this algebraic steps.
Now what about as x approaches 1?
Aha, that's a good one. Let's do that. I like when students create the problem. That was good. All right, same expression. I want to find the limit. X approaches 1. Okay. 1 plus 5 plus times 1 plus 6 is. So we just substitute. We're using limit laws, by the way. You went through all those limit laws? 12. Thanks, Joe. What's the bottom now?
Yeah.
I bet you know the answer then. That was a good question. You came up with the problem. What do you think the answer is to that answer? I bet you know. What's the right answer? There you go. You got it. We said that's not 0 over 0. See, if we got 0 over 0,
Yeah.
then we're playing.
Let's do one of those.
I like it. All right. So when he goes, let's do one of those. Okay. X approaches. How about -2? But this time, I changed the denominator. All right, what do we do? Before you start manipulating, remember I always want you to do this, try to what? Yeah, plug it in. See what you get, because if you get 7 over 0, put 0. You get 12 or 0, I mean, it does not, you get a number, pick a number, but let's just see, I plug in -2, I get what? Ooh, you get 0 on the top. What do you get on the bottom? 0. There it is. They call that indeterminate form. So the answer is not 0, is it? You go, what do you do? It's playtime. You go, don't stop. You go, all right, I got the indeterminate form. I'm going to go back to this expression, and I'm going to use every tool in my algebraic experience to manipulate this thing. Any suggestions? Factor. There you go. So there's the first word when he comes up. It's like things to try. He goes factor. Good on. Good thing to try. You look at something, you go, well, maybe I get factor. And can you factor the top? X plus 2 and x plus what? Can these cancel? Now, take that number, substitute it. What's the answer? -2 plus 3 is a 1. That's your limit. Isn't that cool? Isn't that cool? Now, I was going to pull out the graphing calculator, but I don't need to. If you wanted to check this problem, you're on a test, you're like, I want to make sure I did this right. That right there, since it's simplified, you get this. Isn't that just a straight line? That's a straight line. So I just want to let you know in algebra, this expression, f of x equal to x squared plus 5x plus 6 all over x plus 2 really is a straight line. It really is. Because you all just saw it. What cancels? The x plus 2's cancel out, right? But this straight line has a hole somewhere. It has one little tiny hole. It's infinitely small. Where's the hole? -2. Because this is the original expression. So if I graph this line, everyone, and you all know how to graph the line y equals x plus 3. The y-intercept's what, 3? You rise 1, run 1, rise 1, run. This line is just going like this, right? It just keeps going up like this. But at x equal to -2, when you put that -2 in there, it's like right over here. Right there, there's a tiny hole. Because it didn't exist there. But it's right at that +1. So what's it approaching from the left side?
-2.
You know? It's approaching that +1 value, right? What's it approaching as you go towards -1, -2 from the right side? Approaching that. Does that make sense? So I'll label this. When this was -1, that right there was -2. That's a. It's always we put the. So as you approach x equal to -2 from the left, you're approaching a 1 with a hole in it. As you approach -2 from the right, you're approaching that hole right there. But you're approaching the same number, aren't you? If you graph it on your calculator, will you see the hole? No, because it's infinitely what? Small. You won't spot it. But if you look in table, it'll give you a little message like D and E. It'll say, hey, there's nothing existing there. So isn't that cool? So you can always check it on your calculator. You go, oh yeah, it's just approaching a 1. You can look at these things graphically. All right, great job. All right, try this. See how good you are. Hey, the bottom 0, right? Maybe it's indeterminate form. Always make sure though. What's the top? 9 plus 15, 24 plus 6 is 30? What do y'all think? DNA. That's not indeterminate form. It does not exist. Does not exist. So you go, oh, is that a straight line? No, that's not a straight line. Look at your calculator, you get one of these funny rational expressions, rational function. It's a rational function. It's crazy. It's got a slant asymptote too. But it does not exist as a bridge tree. Alright. Try this one. How about x squared minus x minus 12 over x minus 3. And after you do that one, try this. Minus 3. X squared plus x minus 12. It does look like the same problem, doesn't it? I'm trying to emphasize, always check first before you start manipulating to see if you get 0 over 0. Don't manipulate unless you get 0 over 0, right? Always check. You get a number, that's it. You get something over 0, 5 over 0, D and E. Is this 0 over 0?
-6 -6.
Ah! We already know the answer then. D and E. So that's my point. Like, I'm not factoring, I'm not doing any factoring until I make sure I've got 0 over 0, right? That's when I have to play. And probably get an answer. So hey, it's done. It's not 0 over 0. -6 over 0 is undefined. Hey, also Matt, I did a bunch of over zeros. What if you got 0 over 7 again?
0.
That's 0. That number, everyone, does exist. That's 0. So if you ever get 0 over 6 or 0 over 7 or 0 over 10, that's 0.
I have a question.
Awesome.
What is the difference between like a number over 0 and 0 over 0?
I love it. So 0 is, that's what it's like, defined mathematically as the indeterminate form expression, right? Like a number over 0 we know is undefined with these algebraic expressions. 0 over a actual finite number is 0. But when we're dealing with these limit laws and we have these algebraic expressions, okay? If you get the 0 over 0 scenario as you're trying to find a limit, that usually indicates that somehow, some way, that algebraic expression there can be manipulated and rewritten in another way to allow you to evaluate it. The only thing is, and I think you understand this original expression right here, the actual function, this is a function, it does not exist at the x value of what? 3, right? It definitely doesn't exist there. But it's just the scenario that we determine, we call the indeterminate form. But it's really with these limit laws. That's the only time we're dealing with it, the 0 over 0 scenario. The indeterminate, only with limits. Hey, what do you get on top?
0.
Oh boy, here we go. Doesn't that mean play?
Yeah.
Alright, we get to play. Any suggestions?
Factor.
Factor, alright. So what's the top factor?
X plus 4, x minus 3.
Ba-boom. Knock him out.
Take out x minus 3. 7.
7. Even a final exam, you get ones like this, you know?
And then there's
It's like mid-July, you're like, all of a sudden you're like, oh, let me see if I get 0 over 0. If not, just put down D and E, right? Yeah, what's the problem? I always get a kick out of this. Gets everyone on a final.
Do you always just factor, I guess, if it's like that?
No,
Or is
good
there
question.
other-
There's other ways, and they're coming up. It's gonna be a few more things here, but when we're done here, Joe, it's probably gonna be about 4 things. Factoring, common denominators, conjugates, and then we'll come up with a 4th one and say, what else is there? And I think the 4th one, we'll just look at something. If none of those work, we'll just end up expanding it. Do you know what I mean by expansion? You just start distributing everything. You just distribute everything that they have. They might have it all factored already, and you just distribute and see if you can get the thing to be manipulated. Cool? So that list will grow. I just wanted to show you something. Ready? Yeah, look, you're on the final. Now here we go, it's a natural log, right? But heck, you got a calculator with you. You don't know what the ln of 1 is, you can check it on a calculator. I bet you know what the ln of 1 is though. Natural log of 1 is what? 0. Yeah, a few things it's good to know in math. Without the calculator, you know the calculator would do it. It's good to know e to the 0. And it's good to know ln of 1. What's e to the 0 power? 1. Comes up a lot. Comes up a lot. What's ln of 1? 0. But you can still hit ln 1 on that. So anyways, what are we getting? DNA. And a lot of students were saying they probably make the graph. You try to look at the graph, probably looks kind of funny, and they're choosing other, putting other answers down. There you go, that's it. But I'm with Joe Erwin. Great job with that. Was everyone okay with that? So like, come on, give us some of these other scenarios. So if you have your textbook, great. If you don't, it's all right. I'm going to write these problems on the board. I want us to focus on problems number 11 up to about number 27 or so. All right? They're really good. I put them in your practice problems, so you'll practice on these. I'll try to stay even up because you all practice the odds. Well, we already did one like number 11. We already did one like number 13. Yeah, we did one like 15. How about one like, let me go down this list. I'm looking for it. I see it. And when I want to give you one like number 23. Okay? All right, here we go. This problem, if you want to write down, it was like number 23 from the textbook. X approaches a negative 3. 1 over 3 plus 1 over x all over 3 plus x. And it's an algebraic expression, it's a two-side limit. What's the first thing you'll do? According to limit laws, we're going to try to substitute this thing. But if we get 0 to 0, indeterminate form.
Put the negative sign on the other side.
Oh, yeah. And but if we plug that in there, what do you get for the top numerator?
0.
You get 0. The bottom?
0.
There it is, Owen. So right now we're saying, okay, the limit may exist. Right? Is it indeterminate? There's a way we can manipulate the expression. We can manipulate it. That word I use, manipulate. Factoring's not going to work though. So what do y'all recommend? You got it. Common denominators. Whatever way you like, that's called a complex fraction. So whatever way you like dealing with complex fractions, do it the way you like. Alright, here's the way I'll instruct it. Alright, I just want to get out a different colored chalk. 3 and an x, the common denominator is 3x, right? So I have to multiply an x here and an x here. Over here I have to multiply a 3 and a 3. Okay, let me just draw an arrow. It looks like I have an x plus 3 all over 3x. What's down here? What's this 3 plus x over there?
1, 1, 1.
Oh, alright. Let me make sure. Am I okay with that? This is the idea of common denominators. I had to somehow, I wanted to manipulate this, so I'm going to add these two things together. Well, to get a common denominator, I had to multiply an x over an x, and I had to multiply a 3 over 3. And then when I add them, the common denominator is 3x, and I get x plus 3. Is everyone okay with that? Yeah? So the bottom, it just had 3 plus x, right? But I'm like, but what is it over? It's invisible. What is this just sitting over? They're both over 1, so the whole thing's over a 1. A 1. Now, I bet you know how to deal with that. The flip, shoot. That's what you got to do. So take the bottom here and multiply the reciprocal of the denominator. All right, see what we get. You get x plus 3 over 3x. Put a dot, and like she said, flip that. Multiply the reciprocal of the denominator. And we're hoping something cancels. Anything cancel?
3 plus x.
Knock them out. You can put parentheses around these, they're gone. So this whole algebraic expression is equivalent to this expression, except for the fact that, we know this thing was undefined at -3. But, according to limit laws, this is still going to produce our result. Stick it in there, what do you get? What's the limit?
1 over -9.
That's it. Hey, backup book probably won't write it this way. Even though I changed it when I did a problem like the one in the book. How do they write fractions that are negative? They put the negative where?
At the front.
They put it right in the middle. You can put one, you can put it on the top, you can put it on the bottom, or you can put it in the middle, it's up to you. Just don't do top bottom, you just made it positive, right? Cool. So our list is growing. Factor, a scenario like that, Joe, how about common denominator? All right. And looking back here. All right. Okay. How about this scenario? Nine minus x. By the way, sometimes the author uses t's, sometimes the author uses s's. I just don't want to use s here because s can look like a 5. So I'll use x. And he's got something like this. A 9 minus x 3 minus the square root of x. Find the limit as x approaches 9.
What number is it?
This one is like number 27. It's like, I'm doing like 30. It's like number 27. I'm trying to see if there's another one like it. That's the only one? I'm shocked you didn't get 2 of these, Joe. The only one that's like 27. That's it. And this one's like 27. And don't worry, like, even tonight, if you try 27 tonight, because I put it as a practice problem, and you don't get it, let's do that one tomorrow. I always like to let you kind of play with it first. All right, plug in 9, what do you get? All right. We gotta manipulate this dude. Now, there's one way that works every time with this scenario. Because you might look at it and go, it might not look factorable to you, because you don't see the typical x squared minus 9s. We may come back to that, okay? Because some of you may prefer that. But I'm going to look at this problem, and I want to give you a technique that's new. Factoring, all right, maybe I'm not aware of how I can factor that. Doesn't look factorable right now. We'll come back to that. Common denominators. Can't done work, right? I don't see any fractions. But multiply a conjugate. Have you ever done that before? So I'm going to add that to a list. It's another strategy. It works definitely in that scenario. Joe would work on number 27. Multiply what we call a conjugate. What's a conjugate? It's simply the opposite. And you go, of which part? And when you got this guy and you got this one, multiply the conjugate of the radical. How about that? She said bottom. I like that because you saw that pick in the bottom. Look to see where you got the square root. How about that? Identify where the square root's hanging out and multiply the conjugate of that expression. So this word conjugate, what's the conjugate of 3 minus square root of x? The only thing is I got to do it on the bottom and the what? Top. And here's what I want you to do. Leave the top alone. All right? Let me say, leave the top alone. Leave it as is. I don't want to make. We're not going to make this problem as difficult, more difficult than it is. It's the bottom. We wanted to make the bottom pretty. Focus on the bottom, where you did the conjugate. That's where you need to focus. Foil that thing out. F-O-I-L.
There's 9 over x.
And what happens? When first, outers, inners, last. F-O-I-L, right? What happens to the OI? They just go away. Because look, when you do the first, you get the 9. You do the outers, you get plus 3 squared root of x. You do the inners, you get minus 3 squared root of x. Bye-bye. And then the L is that minus what? Square root of x times square root of x is just a x. And a lot of you just do that mentally. So you have to write all this stuff, which is great. So I'm going to rewrite this so you all see it. 9 minus x, 3 plus square root of x. It's all over 9 minus x, and we get to cancel the what? Now it's time. Take it and what? Put it in. What's 3 plus square root 9? Now you may want to investigate this. Look at that graph with your calculator. You'd probably see it approaching a 6. The only danger is sometimes graphs like that may look a little weird. Just because of the nature of how it's set up. Conjugate. So we got our list is growing, but that one doesn't go further than this. One more type. Cool. Conjugate. Now does everyone have this? Because I want to back it up. And I bet you some of this class had another idea and it works. You sure? Yeah? All right, back it up, back it up, back it up, back it up, back it, come back here. Did anybody have another idea?
Is it like 9 minus?
I heard it. What was it?
Just factor the top.
He goes here. What's funny is that when you look at that and you go, factor. They don't put those problems in algebra books. But you can factor it. See, I mean, how do you factor this? Just tell me, how do you do that difference of squares? It's x plus 3 and what? X minus 3. It just doesn't look like something. Absolutely, you can factor that. Watch what he's gonna do. He's gonna factor this dude. Da-da-da, da-da-da. It's a difference of perfect squares. Square root of 9 is just a what? 3. Make one a plus, make one a minus, but what's the square root of that thing? Root x. So feel free on the test. You like that better? You might find that quicker? You're like, psh, I'm done. Plug in the number. No one say that? So here, just so you're okay then, how would you factor that thing right there? If you wanted to. 4 as a difference of perfect squares. 4 minus a what? Root x, and a 4 plus a root x. I know, they don't put them in algebras. But we can get the calculus to let you see that. But you definitely can factor that. Great call. Yeah, I don't need to play with that conjugate. Okay. Finally, when I get to grab a problem that's actually in the book because it's even. This is number 30. All right. So you can write that number 30. Let's do that one. The limit as x approaches -4. Here's our repertoire of things to try. Square root of x squared plus 9. Boy, I wish we could simplify that, can we? No. Can't simplify that thing. -5 over x plus 4. This stuff's fun. Well, let's substitute the number. Let's see what we get. If we get a actual finite number, we're going to put that as our limit. So 0 over 5, 0. 5 over 0 does not exist. What do you get?
Wait, isn't the square root of x squared plus 9 just x plus 3?
I wish. You're thinking of this. I wish. You're thinking of that. Which is what? They got a list of like the most common misconceptions in math. Do you know that's number 1? It is. See, that's x plus 3.
Yeah.
It's actually the absolute value of x plus 3. That's just can't simplify. Isn't that funny? Unless you're in a complex number system, I'm with the i's. You're doing x plus 3i.
But if you split the two, if it's the square root of x squared plus the square root of 9.
I wish we could do that. We can't. I know.
The conjugate on the top.
Yeah, that's gonna work. That's gonna work. Great call. So let's try the conjugate. You hear? Let's do the conjugate at the top. I do want to point out though, it looks like it gets simplified, but you what? You can't. Hey, it's number 1 on the list of what? Students' misconceptions of some expression. That's number 1. They look at it and go, you can make that x plus 3. And you're like, nope, I wish, but nope. This right here does not equal what? X plus 3. You wanna just let's easily show why. Use the number like 1. I want to put a 1 in there. Is the square root of 10 equal to 4?
No.
See, there you go.
Okay.
There you go. He's like, that doesn't work. Very good. But then when I heard an idea, look at our list, factoring, common denominator, conjugate, he goes, go with conjugate. Great idea. The conjugate of which one? The top. He looked for the radical. And he saw the radicals up here. Oh, it's going to be long. Who cares? Just make it long. Square root of x squared plus a 9 plus a 5. Now notice I didn't change that plus in there. So let's see that. Just that guy. And what else do I go to on this bottom? Oh, it's going to be long. Now I want to say this over and over, emphasize this. Leave the bottom alone. Everyone, you got me? Leave the bottom. Don't go foiling out the bottom. You'll make a mess. It's the top you're trying to what? Prettied up. You're hoping you get the top all prettied up and it knocks out that x plus 4. All right, here we go. FOIL. What's x squared plus 9 with a radical on it? Times another root x squared plus 9. What's going to happen to the outers and then the inners? They're just going to cancel. So when there's the f of FOIL, the O and I are going to do what? Cancel out. We know that happens every time in the conjugate. So get to the L. It's minus 5 times a plus 5. Alright, we get all this all over what? There's an x plus 4. And there's a square root of x squared plus 9 plus a 5. In the parentheses, we are not going to FOIL at the bottom. What's the top simplified to? Let me write this again. Limit x approaches 4. Limit x approaches 4. X squared minus 16. Daggone it, that's still give me 0. And when I'm still in the indeterminate scenario, but I bet you know what to do. And I'm still in the indeterminate scenario. Ugh. Any suggestions? Now you factor, look. Isn't that cool? We went from here, now we're coming back to here. Factor the top. X plus 4, x minus 4. Boy, we're going to get an answer now. There they go. Opsh, opsh. You got this what, x? We never... So where do students get lost in here? I grade tests. I see students, they know to multiply the conjugate, right? The error is they start expanding the other thing without the radical. They start foiling it all out, and it gets crazy, and then they can't cancel anything. They get to here, there's nothing to cancel. So now, what are we going to do for our last step?
Professor,
Oh,
that should be minus for limit
oh,
x.
you're the best. Where is that? Right
X,
there?
Yeah. No, x, limit x approaches minus 4.
Oh, right there?
No, limit x approaching 4. It should be negative 4.
Right there?
No, on the other left, limit.
Limit as x approaches negative 4.
Oh, thank you. Thank you. You guys are the best. I wonder, like, that wasn't a 4, that's a negative 4. Hey, thanks. So now, let me write this again. The limit as x approaches negative 4, and you got a x minus 4. The bottom has a square root x squared plus 9 plus a 5 with a big old hat on there, right? So what happens when you plug in negative 4 at the top? We get negative 8. And how about the bottom? That's an ugly looking radical. I felt good.
Not every whole thing.
It was only the first part? So when this radical here is only here, yeah, that would have made it irrational. And you get 16 plus 9, 25. The square root of 25 is 5. The 5 plus the 5 is the... So there's our numerical answer. Can we reduce it?
Negative 4/5.
Nice. There's your limit. There's your limit. So there's our list.
That's it. Like I said, there's
Nah, there's one more.
I don't understand, that was fun.
There's 4. So when I'm going to one like number 17. Okay? So, let me put this up here. This one, everyone, like number 17. Because I want you to practice 17. The answer's in Bob. Bob is back a book, right? Yeah, Bob, I have the answers, you can check it. So let's make one, just kind of, don't go too far off, but something kind of cool, all right? First of all, I noticed they used the letter H. Okay, I'll use H. So when as H approaches a 0, they got a negative 4 plus H squared. They got a minus 16 all over H. At least I can't mess that one up, Art. This is just 0. Negative 0 to 0, right? Thanks again, everyone. Okay. Well, the first thing we do is we plug into what? Plug into 0. Well, I'm going over here. Factor, common denominator. Conjugate, So what's another way? We just expand it. And what do I mean by expand? Multiply everything out. Let's try that. There we go, well, how about that? Yep. Get rid of that square and just expand it all. So what do you get if you expand it? 16, oh, first I should write it like -4 plus h, -4 plus h. Alright. -16, -8h plus h squared minus so far so good? Anything go out?
Cancel out the 16.
Nice eye. Ah, they go away. Oh, now we're safe. I mean, I'm still getting 0 over 0, indeterminate form, but I think you know what to do. Factor out the h. See, we're getting 0 over 0 now, but they're like, factor out an h. Get this h, get this h, you get -8 plus h. Substitute what number? Whop. What's -8 plus a 0? Negative what? Okay, cool. You're an expert. Those are the 4 scenarios. Factor, common denominators, conjugates, expansion. And you can cover them all. Hey, before I do that quick lesson on 2.4, I want to tie in the very first problem I did. So you'll see this at the beginning of that last video. You know what we were trying to do? Remember we just kept getting the slope yesterday? It was kind of tedious. We did from 2 to 2.5. Then we found the slope between 2 and 2.1. Then we found the slope between 2 and 2.01, remember? So in reality, you know what we were trying to do? We were trying to estimate the slope as x approached what number? 2. So we got closer and closer to 2. So I want to write that on the board. So, and this is funny. The problem we were doing, this is how I wanted to end the 2.3 lesson. You go what? I'm going to take the problem that we did from 2.1. It was number, oh gosh, I forget. Was it number 5?
Sounds right.
Alright, and I'll write the question. This is really what we were trying to do. We were trying to estimate what was going on with the limit of all the slopes as you approach the value of 2. Okay? Yeah, so you'll see this column, you see this at the beginning of that video. We were trying to just do this, and we're like, okay, and we just kept playing around with this thing. Well, what's the formula for slope? Y sub 2 minus what? Y sub 1 over x sub 2 minus x sub 1, right? Alright. So we're trying to do that for f of x minus f of 2 all over x minus 2. You know? Y sub 2 minus y sub 1 over x sub 2 minus x sub 1. This is what we're doing. By the way, in the book, he used t's. I'm just changing t to an x. Is that what I go with that? In the book, he used t's. Now, this was the function. I do have this memorized. I remember this from yesterday. You probably remember. This was the function. 40x minus x squared. No, minus 16x squared. It just had t's. T for time. So if you want to make these t's, you can. I just don't want the t's to look like pluses. So that was the function. But what we were trying to do is find the limit as x approached 2 of those slopes, right? What's going on with those slopes? So this is what we're doing. Well, I just want us to look at this problem now. All right. What was f of x? So what? The only thing is, can you help me out? What is f of 2? All right, so is it 16? I mean, we just have to plug in a 2 here to figure out what f of 2 is, and we're getting 16. 40 times 2 is 80. Minus 16 times 4 is 64. It's 16, right? So this is what we were trying to do. There's your slope formula. We were trying to find the limit as x approaches 2 of the slopes. 40x minus 16x squared minus 16. All right. Take a couple minutes. See if you can find that limit. So I'm plugging in right now when I'm getting 0 to 0. Right? So then when this is just like number 5 and 2.1, we are trying to estimate the slope. My point is we should get that number we figured out when we estimate it. When we estimate it, we should get that same answer. Well, I plug in 2 over 2, guess what I get? So any suggestions? Here's your list. What do y'all think? You got an idea?
You make, instead of subbing 2 for x, you make it a point that's really close to 2.
Oh, I got you. So he's going back, he's not using algebra, he's not using the limit laws. What he's doing is he's estimating it numerically. That would work. I bet you'd figure out the answer. What he's saying is he's like, what's the number really close to 2?
2.001.
He goes 2.001, 2.001, 2.001, and boy, you're going to have a really good idea what that integer is. And then just go to the closest integer. Heck, that would work, but I'm talking about this. Let's choose one of these things. So any suggestions? Factor. So we're going to try to factor this thing. All right, so let me write this again. Let me go to the first one. When you factor, I think it's a good idea to the highest power first, right? Is everyone okay with that? In fact, I'll be honest, I can't stand when x squared's negative, so I like to make it positive. So are you okay if I just, this is just me, I don't like that daggone thing being negative. So I'm just going to factor out a negative, so what would be in my parentheses? 16x squared minus a what? Is everyone okay with that? It just makes it easy to factor. Now, can I factor anything else out of the top? They're all even. Does 16 go into 40? Not perfectly, but 2 does. Does 8?
Yeah.
Let's factor out an 8. I'll make this problem easier to factor. Negative 8. So we're factoring away, everyone. 2x squared, what would be here?
5.
Minus 5x plus
2.
2. The only problem is, the only problem is, do y'all know how to factor that dude? Can you factor this guy right here? What do y'all think? Almost done. Oh, we're gonna get this answer. This approaches 2. There's a negative 8 still sitting there. Don't trash that negative 8 though. It didn't cancel. Alright. What's this factor? I bet you one of them's an x minus 2. Y'all agree? Who's the other one? 2x minus 1. Although you can check it for all I know. So what cancels? Now what do you do with this 2? Alright, what's negative 8 times 4 minus 1? Is this what we got last time? We sure did. Remember? I'll put the feet per second. Do you remember this? We estimated the instantaneous rate of change. Well, that's the exact instantaneous rate of change if this represents position. So this was height. That's the exact velocity at time equal to 2. Isn't that cool? Welcome to calc. That's what's neat about this stuff. We're building on this concept. We don't have to do this old little like plug-in number near it. We're getting more precise. We're getting up to here now. And we're really saying, hey, use the limit laws. You can plug this stuff in here. You can algebraic manipulate it and get your answers. Now we know how to evaluate instantaneous velocity from position. Really kind of cool. Sound good? All right. On the rights. That's why I just wanted to tie that in. I thought that'd be cool. All right, 2.4. And what's this title called? The precise definition of a limit. Well, in 2.4, you're like, how do you define a limit? So I'm going to write this down, Aaron. This is on page 110. He writes something like this. If 0 less than or equal to absolute value of x minus a is less than some delta, then f of x minus L is less than epsilon. And that's delta and that's epsilon in terms of the Greek letters. Delta and epsilon. All right. And they got more stuff on this. So I want to tell you the page, if you want to read everything else, they say let f be a function of phi on some open interval, et cetera, et cetera, et cetera. And we write limit as x approaches a of f of x equal L. This is what's going on. But doesn't this look what? A little confusing? All right. We won't spend much time on 2.4, it's okay. But I do want to hit at least just one problem to work from this. All right?
Is that a D?
That right there, it's actually a delta. It's a Greek letter delta. Feel free to call it D. And that's epsilon, feel free to call it E. But I want to tell you what they're representing. Very, very, very infinitely small values. Someone got that? The delta and that we're saying they're representing this and that. Delta and epsilon. Some mathematicians call these, if you do the problems in this section, they got some proofs. They call them delta epsilon proofs. Right? The only thing is, I would go off all day. I'd spend a week on this section with you. If they said in our curriculum, if they said, I want you to spend 6 hours in this section. Well, they allotted me about a half hour. I said, a half hour? And we're going to have to do some math proof? I was like, no. We'll just talk about the definition. Make sure we get the definition down. True, yeah. So, I mean, you can go real heavy in this section if you're going to be in pure mathematics, but absolutely, if they're only putting a half hour, that's as well we're going to spend it with this. So there's this proof, but it doesn't make so much sense, does it? So I got to talk about where's the delta, where's the epsilon. So I'm going to come back. Can I erase this? So you'll see this, and when this is written, this is on page 110. But I want to show you in terms of where's the f of x, where's the delta, where's the epsilon in the graph. Okay? So, here's the problem I wanted to show you. All right. They got this. If you use the graph, to find, and Joe, that's a delta. Use the graph to find delta. If 0 less than or equal to absolute value of x minus 3 less than delta. Well, I just put a big law here. In this problem, you're going to use the graph to find delta. If 0 is less than this absolute value, there's another way you can say that when the absolute value of x minus 3 is distance between x and 3. That's another way you can say that to yourself. The distance between x and 3 is less than delta. Then they got absolute value of f of x minus 2 is less than 0.5. But they got a picture of a graph. All right? And in this graph, there's the function f of x. All right. Here's the x value 3. I won't even put the 1 and 2 down. There's the y value 2. So let's see how 3 is lined up with 2. By the way, everyone, if this is f of x, I think you all know what's the limit as x approaches 3? 2. Yeah. So you all see this? You all see that, right? But we're just talking about this precise definition here. This is 3 and that's 2. They want us to talk about this funny thing, delta. All right. So now, what else do they have in this image? They showed this over here. At x equal to 2.6, they told us. So they gave us little tidbits about this function. At x equal to 2.6, the y value is 1.5. And at x equal to 3.8, way over here, the y value is 2.5. All right. Make this look a little better there, because I want this to be exactly, that's a half from there and it's a half from there. Ah, that looks better. Nice, there we go. All right. don't let this problem intimidate you, not at all. We're just looking for this delta, right? Now, I want to point out, where's delta? There's a delta and there's an epsilon, okay, everyone? Delta is this very, very small distance from this value 3. Delta's down here. So delta could be from here to here, or it could be from here to here. Well, where's this epsilon distance I was talking about before? Epsilon is that distance right there. So can you tell me what they're talking about for that epsilon? What's 2 minus 1.5? That's why they put a 0.5 there. So the epsilon distance is over here, from that 2. Is that distance epsilon? So from here to here, what's the distance from 2.5 to 2? 0.5, okay. What's the distance from 2 to 1.5? 1.5. So there's your epsilon distance, but your distance from 3 to a 2.6, or 3 to the 3.8, is referring to this delta expression, okay? So here's the only thing we got to figure out for this math problem. For our answer for this delta, are we going to use, everyone, what's 3 minus 2.6? 3 minus 2.6 is 0.4. What is 3.8 minus 3? 0.8. The question is, which one of these two answers are we putting for our answer, according to this math proof? All right, we got to figure that out. We got to all logically figure out, are we going to use 0.4 as our answer? Use the graph to find the value of delta, such that this would be a true statement. Brilliant. She knows. She knows. She goes, it's this guy. This is our answer. We're going to use, by the way, in any problem like this, I can make 100 in a row. You always use the smaller of the two radii. Now, I'm talking about radii, like distance from here to here. If these are your two values that we're trying to figure out our delta, you always use the smaller of the two in terms of the distance. And 3 minus 2.6 is smaller than a what? 3.8 minus 3. It doesn't matter which way you subtract, you can just do absolute value. Do you want to know why? She saw this. Very good. She saw this. This is 0.4. We're using that because, I mean, look what happens here. This is 0.8 away. If you went 0.8 away this way, what would you get to? What's 3 minus 0.8? I'm going to write it down. You get a 2.2 here. And I want you to see where that hits the graph. This x-ray at 2.2 hits the graph right here, right? Which puts you here. Are you still within a half from 2? Are you still within a half from 2? Can you all see it? No, you went over that half distance. This statement, for it to be true, always had to make sure this was less than what? Less than a half. But if we use the what? If we use 0.4, so we're going to cross that out. Sorry about that. You're not it. Let's use 0.4. Okay, if you go this far, how far are you away? 0.5. Now go 0.4 this way. What would you go to? 3.4. Go up here. Are you within a half distance? Yeah, we're still within a half, aren't we? It says less than. We're still in there. So, hey, moral of the story, keep this simple. I could give you 99 more of those in a row. And you're looking for the delta, which one are you always going to choose? The what? The smaller, the closer one.
But where'd you get the 2.6 and 3.8?
They were given, great question. They were given in the problem. And that's the one problem I like to focus on. It's this idea of what they're going with this precise definition. I mean, reading in the math proof and stuff is they're saying, the idea of limits is, if you keep doing what? If you keep shrinking this distance, what happens to this distance? I mean, what happens? Like, this is 0.4, but what if I went closer? If you went closer to a point closer to 3, what happens? Up here. I'll get this out of the way. Here, get these out of the way. And when right now I'm going to erase these. If you go a little bit closer to this what? This tree. Let me really highlight this now. Right, this is a what? That's a 3. All right, get the other stuff out of the way. And when you, the whole idea of this concept of limit is, if you went really close to here, aren't you closing in on here? You follow me? It's that simple. That's what we're saying. The more tighter you bring it in here, you're getting closer to what? The actual limit. L is limit. And if you just keep bringing delta, and we're saying, as long as you keep getting this distance, you can't be a distance of equal to 0, but you're always what? Very, very as close to 0 as you can. Infinitely small. Cool. Thanks. Hey, you okay if I don't even put that problem on a test? You know, hey, trust me, I could give you 99s in a row. Wouldn't you get it anyway? But sometimes, I know. So I probably won't even put a problem in that section like this. But thanks for bearing with me on that. I just want to make sure you're good with that. We get a half hour to lot for us to do that stuff, right? Cool.
What's the use case for this?
Oh, great question. That's the whole idea. I mean, mathematician, I used to be on a listserv, and it would pop up every year. The title would be Delta-Epsilon proofs. And which teachers what? Would do this, and this, and I think this is great. We should show this. And the one area I would say I would totally agree with them is, let's say a student in this class is going to be a pure mathematician. Now, pure mathematician, that's all they're going to do is math proof. That's all they're going to do in their undergraduate degree, probably their junior and senior, a lot of math, sophomore year too. Master's degree is going to be all pure math, which is all proof. So they might get into this stuff. You start talking about, it's just a theory behind it. But if you say beyond this, are you going to need that for calculus 2? No. Are you going to need it for calculus 3? No. Are you going to need that for a differential equations class? No. But that would be the only one. If we're looking for a benefit, is a student who's really into pure math and curiosity about the theoretical realm there. That's it though. That's it. I mean, seriously. Other than that, that's why you notice, again, now you know why 30 math colleagues in my math department decided, how much are we going to allot to this? They didn't give it an hour? No, not even an hour. They only went with what? Half hour. They're stopping. Just a half hour. Just do something. I'm like, okay, we'll talk about it.
Isn't this like the difference quotient?
Yep, it's just like the difference question. That's coming up. That's coming up. We won't get to it today. So, hey everyone, thanks for bearing with me on that. Unless you wanted me to put that on there. You're like, no, put it on there. We'll just take the smaller one. Fill it up. Yeah, I know. Hey, last thing we're doing is continuity. Again, this is not a long section. It really isn't. Which one was big? 2.3. That was a lot of algebra. This one ain't that big, but I want to go back. I want to see if we can come up with a definition for continuity. So I'm just going to make a picture like I had the other day. I just had a graph like this, right? I'm going to put a hole here. And when this is x equal to 1, and this is the y value 2, okay? I got a hole here though. Does everyone see my hole? Now I got a dot right here at 4. My question is this, before we get into continuity, 2.5 is on continuity. You ready? What do you know about the limit as x approaches 2 from both sides? All right. For the limit as x approaches 2 to exist from both sides, the limit as you approach from the left side has to equal the limit as you approach from the right side. All right. As you approach x, not x equal to 2, x equal to what? 1, I apologize. So as you approach x equal to 1 from the left side, what y value are you getting closer and closer and closer to? Where that distance, I use delta, right? Delta is like infinitely small, delta is close to a 0, right? From here. But you're getting closer to 2. Now delta on the other side is close to 0. You're getting closer to a what? 2. So what's this answer? Does everyone agree? If this is f of x here, I forgot to put the f of x here. Let me just step away. Does everyone agree for my graph? Is this true? Yes. For that graph right there, we know that. True? We're going to come up with a definition for continuity. Like, let's come up with a statement that says, this is what's necessary for a function to be continuous. Continuous means connected. Connected. C-O-N, C-O-N. Continuity? Would you think connected? C-O-N, C-O-N. Every time you hear the word continuity or continuous, think it's got to be connected. Well, everyone, is this graph connected at x equal to 1? No. So let's talk about it. What would simply make it connected? It's that daggone dot. It's way up here. Where would it have to be? Aha, so we're saying, get out of here. For this thing to be connected, this hole would have to be what? Filled in. True? Okay, I'm going to do it right now. So if we're trying to define continuity, and for a function f of x to be continuous at x equal to 1, because everyone, can you tell it's continuous everywhere else? I'll put an arrow. Isn't the function continuous everywhere else? Let me make sure that doesn't overlap there, because then it wouldn't be a function, right? You just put an arrow like that. f of x, in order for it to be continuous at x equal to 1, the limit as x approaches 1 of f of x would have to equal, fill in the blank. What do you think? Someone's going to come up with this. Remember, it wasn't continuous, right? It was a hole. It was way up here. But we said to make this continuous, we'd have to have this hole what? Filled. So I'm putting a dot here. Now, do you notice that one? I'm playing around with f of 1, right? That's what I'm doing. I moved f of 1. This is x equal to 1, but I moved f of 1. So we're saying, for a function to be continuous like this, at x equal to 1, the limit as x approaches 1 of f of x has to equal f of what number? There you go. Thanks for being with me. This is what we're talking about. This is what makes a function continuous, by that statement. Now, we could put one in the textbook like that. We would just have to change number 1 to some letter. You want to make up a letter? Give me another letter.
H.
H. Here goes, all right, H. Oh, don't use H, because they always use H for difference quotient. How about C? Will C work? That one? All right, so here we go. Let's make this statement now for all functions. The limit as x approaches C of some f of x, then what would have to be true? It would have to equal what? F of C. Isn't that cool? I know, I was like, maybe I should have them do that on the test. I just wanted to show you that. So,
That would be anything.
that's funny. What do you think? I was thinking about it, Joe. I was like, yeah. I think it's more fun, but I noticed how you came up with this. That's what I want you to see. Like, in math, sometimes you go, how do you define something? This is how you define it. So that's why they put the continuity section after what section? The limit laws and limits. It follows limits. It's the idea. You need limits to define continuity. Do you follow me? To say everything will be as long as this is true. The limit as x approaches every value c on the function of f of x will equal to what? F of c. Cool. Awesome. Hey, let's do one. But I want you to focus on where's the function discontinuous. Alright? Where is f of s discontinuous? 3 more problems, and I want to make sure we do 3 more. A long section. Alright. Are you ready? Some of this class is going to be quick. I want you to list the x value. So I should say at what x value? At what x value? Is f of x discontinuous? What should we do? Should we graph it? I mean, should we go through the graph and all this? Hold up, I think you all know. Where's this graph not connected? You bet. Don't make it harder than it is. Do you all agree? We have knowledge of graphs like this. This graph is undefined at what value? That means it would be nothing existing there. Well, the graph has to be continuous everywhere and have any breaks. Well, there's a break at 7, so what's the only answer? At x equal to what? Joe, I think we should put that in the test though, right? Yeah, right? You agree? Hey, the only thing is, you know what sometimes people do? They think it's at -4. -4 is okay, you all agree? That the function exists there. It's just the what? Where they call it, there's an asymptote there, isn't there? So focus on the denominator, right? And heck, if that denominator had 2 expressions down there, then use both of those. You know, if this bottom had a what? X minus 7 and an x plus 3, what would be the other value? There you go. That's the idea. Alright, here's my next one. I want to go to page. This was a good one. This time we're going to put a number down. Alright. Everyone, this is like number 45. It's on page 129. like number 45 on page 129. We change directions. For what values of C? Is f, function f, everyone, continuous on the interval negative infinity to positive infinity? Question mark. Well, what value is C? Alright, they gave you a piecewise, everyone. They got a cx squared. And they got a plus 3x there. Alright. And x squared, oh, I apologize, the x cubed. X cubed minus cx if x is greater than or equal to. I'm wrong on the side. Are those trees? Yeah. I apologize. There we go. Cx squared plus 3x, x cubed minus cx. Now everyone, if I hide these, do you agree these things are nice smooth curves? These are cubics, these are quadratic, aren't they smooth everywhere? So really, to make this thing work and continuous everywhere, we're really concentrating on what's going on at what x value. What's the critical value? 3. Do you all agree? Everywhere else, this thing should be safe. But we're trying to solve for what variable? C. So let me reiterate this, and you're going to give me a suggestion. I'll make this problem a very easy question. I mean, I'm talking, we're not even going to make a graph. I just want to make this thing continuous everywhere. Well, that's a parabola. Even though it's got a constant c in here, make that a 2, a 5, and 8. That thing's going to be nice and smooth everywhere. Then that's a cubic function. We're only worried about it this what? The 3. We want to make sure the function is connected at x equal to what? 3. So what's your suggestion? Insert 3. Substitute x equals 3 into both equations and solve for what variable? C. Someone got that? Very good. Let me say this again. Simple math problem. It may look confusing. We're like, let's take the value of x equal to 3, plug it in there, plug it in there, plug it in there, plug it in there, leave the c's, set them equal to each other, and solve for what letter? See? Because that means the two values are going to be the same y values, right? This y must equal this y at x equal to what? 3. Does that make sense? The two y values must be equal at x equal to 3. Do you follow me? Alright, let's do it. Plug in a 3 in here. What do you get? C times 3 squared plus 3 times 3 must be equal to, okay, I'm done there. What's this side? 3 cubed minus the c times 3. Solve for c. This will work. Alright, what's 9c plus 9? Is that right? 3 cubed.
27.
27, thank you. How do you solve that? 12c? What's 27 minus 9? My answer is 18 twelfths, unless we can reduce that. Can we reduce that? What do y'all think? 18 12? 3 heads. Or 1.1? 1.5. Now, how could you check this, Owen? If on your test, you just wanted to check this, and you got like an extra hour, I guess you could pull out your graphing calculator, if you wanted to. Make x what? Make this c value, make this c value a 1.5, and a 1.5, graph the parabola, graph the cubic function, and what should happen at x equal to 3? They should meet. Right? Unless you want to graph piecewise functions. I can show you that with calculator. We're all like, don't go through that, we get it. Hey, can't you do 100 of these in a row? What's the idea? We're only worried about here, right? There you go. Okay, last problem. You know what I wanted to do last, do you remember? It was that problem I forgot last class, remember? The piecewise one. Let me do one of those. So when I'm looking for one in this section, I know they've got one. And there it is. That one. This is number 41. This is on page, it's actually on page 128. All right, here it is. Now, what values of x is f of x discontinuous? Okay. And when f of x equals 2 plus x squared. Four minus x. If x is less than or equal to 0. If 0 is less than x is less than or equal to 2. And my last one x greater than 2. What values of f is f of x discontinuous? Any suggestions on how to do this? Any recommendations? You do this on the test. What do you recommend? I bet you all have great ideas. Look at this thing, it's a piecewise function. We saw this earlier today. We saw it with the limits, right? What was our strategy? Graph. Y'all want to graph it? Yeah, let's look at the graph. What would mean that it's continuous? Connected, right? If it's any broken piece, then it's not going to be what? Continuous. That's all we got to do. Will that work? Now when we're done, I say we look for easier ways. Does that sound good? That's how we're in class. So let's take this. All we're going to do is make the graph. We know how to make the graph. Let's make the graph. Make the piecewise graph. But when we're done, let's look for easier ways that you could say, wait a minute, you know what you only have to do? You really only have to check the what. See, I want to think about it. For continuity, we're only concerned about, aren't these smooth graphs? Yeah, it's a smooth straight line, that's a straight line, that's a parabola. We're really only concerned about what x values. X equal to 0 and the x equal to 1. 2. So some of you might find it easier to just go, why don't you just check the zeros for these two, x equals 0, and check 2 for these two, and make sure they match. If they don't match, it's not connected. Right? For it to be connected, y value's got to equal y value. True? But I'm going to pretend like, hey, if you like making graphs, it works every time. Here it comes. All right, 2 plus x squared, I want to make a little table. What's going on at 0? 2, give me a number less than 0. Negative 1? What's 2 plus negative 1? All right, 0, 2. 1, 3. There goes the parabola. Ooh. All right, make a little table. 4 minus x, plug in 0, what do you get? 4. Plug in 2, what's 4 minus 2? 2. All right. Straight line, right? Hey, where's the hole? Where's the hole? Where's the hole in the second one? Where do I put the open hole? The open circle?
0.
Yeah, I want to put it right there. And let me just make sure you can see that. I really should put an open circle, all right? Open circle, closed dot. I already know one x value. Can we put it down for answer? What's one of the answers? Check it out. Where's that thing broken? What x value? Function is discontinuous at x equal to 0. Do you all agree? That's my point. That's how fast we can figure this out. All right, good. But we also got to check this what? 2. So on one more, make the table. What's going on at 2? You plug in 2, what do you get? 2. You plug in a 3, you get a 3. Aha. But it's got an equal sign. But this thing was already closed up. So when do I put an open circle over a closed dot? What happens when you put an open circle over a closed dot? It stays what? It stays closed. I'll say that again, look, I'm putting an open circle over something that was already closed, it stays closed. It's just still sitting there. And then at 3 you got up to a what? 3 and it just keeps going up. So everyone, what do you think? Is the function discontinuous at 2? No, it's continuous. Continuity, continuous means connected. Cool? Awesome. Hey, and in terms of L and C, everyone, if a function with limits, if a function's not continuous, can the limit exist? I think so. So first of all, if a limit exists, do you think the functions will be continuous here? Yeah. True? Can you say, this is a true statement. If a function's continuous at a point, the limit must exist at the point, right? Do you all agree?
Yes.
That's a true statement. Did you know you can write the contrapositive? It means you can switch this around and put the words not. So I'm going to make another statement. Not L would have to imply what? Not C. You can write it that way. That means if a function doesn't have a limit existing, then what's going on? The function is not what? Continuous. Hey, one more thing before you leave. That graph. Great job with the graph, right? Is everyone okay with this? Guess what's going on later in calculus? We talk about a word, differentiability. See, that's continuous there. But differentiability, we're talking about how it has to be nice and smooth. And the idea that the slope from the left has to equal the slope from the right. Now, can you see the slope there? Isn't the slope negative? How about the slope from the right? It's positive. So that's our next topic that's coming up later. Is the function differentiable at 2? No. That's a later topic, because slope would have to equal slope. We can see, slope's negative, slope's positive. But, we just finished continuity, is it continuous? It's definitely continuous, it's connected, right? It's just a corner. That's not smooth. You follow me? Awesome. Hey, and before you go, who can hit it? Who had a fast way to do this problem? Without the graph. Could you do this problem without the graph?
Yes.
What'd you have to check?
Check 0 and 2.
Because you check the 0, do the numbers match?
No.
You plug in 0, you get 2, you plug in 0, you get 4, and he goes, okay, that's one of the answers. Then, like he said, you plug in 2 here, and you plug in 2 there, but do those match? Yeah, 4 minus 2 equals 2, and you go, okay, that's it. And you're done the problem. And that's your work. That's all you'd have to show, I'm serious. Okay? So if you're a hater of graphs, or you just want to save some time, do it that way. Have a great one. Super job.